He still have the hiccups and I still don't. Anyways,
This last word. Okay, you ready? It comes back to haunt you. Is what it is.
I bet she won't even go to the wedding. I don't know. She didn't text me last night. No, they broke up, so I wouldn't worry about it.
I got 19. Does that sound right?
Other than oh, the rehearsal dinner? I'll be back.
Oh, that's 20. I didn't count it. All right. Make a choice. Got like a 25% chance. Okay, make a choice because I'm going to click the button. Think about what the word termination means.
Oh my God. Now you're playing. Yeah, I didn't get it.
Okay, yep, it's C. Nobody picked E. Sad. Okay. Why is it C? What happens in termination steps? The free radicals get used up. They're gone. All right, so here's a propagation. What's the propagation step? Should I add all these guys?
It's always
Oh, I'm hot in my office with my sweatshirt on. Or it's okay, I'll jump around and do backflips for you. Kill myself. Then I'll wake up and it will be warmer. Okay, we're at 20. I'm kind of spacing out too. Okay, yep, it's B. What kind of step is A? If you have no free radicals and you make free radicals, initiation, starting it, okay? Propagation is where it just keeps going, okay? So it's B. Okay, so the last thing we were going to talk about was kinetics. Kinetics is where you have a rate law or a rate equation. Okay, it must be determined experimentally. Okay, you can figure it out from a mechanism, but if you just know this plus this gives that plus that, you can't figure out what the kinetics is. You have to do a study to figure it out. So you remember in general chem, you would have those tables and they would tell you what the rate was as the concentration changed, and that's how you figured it out, okay? We're gonna figure it out by looking at mechanisms instead, okay? Okay, a reaction coordinate diagram. This is something that I think most of you feel unfamiliar with. The first thing you do to draw a reaction coordinate diagram is basically a picture, graphical representation, if you will, of how the reaction is progressing. So I'm going to make one up, okay? We're just going to do a simple one. All right, so here is our graph. You have a graph. And up here, it will be potential energy. Does that ring a bell? Okay. And then down on the bottom, there's a couple things that people put. The main one is progress of reaction. Okay, RXN is my shorthand for reaction if you haven't picked up on that or I haven't told you that yet. The other thing I'll see is sometimes people will put reaction coordinate. Okay, but I tend to write progress of reaction. It's how the reaction has progressed. Okay, you're going to start with your starting materials. Okay, and typically we draw a little curve, and that's like an energy well where your reaction mixture is. Okay, in order to get to products, you have to go basically over the hump. Okay, so down here I'm going to put SM for starting material. What do you think of that? Okay, and then you're going to have mountains or humps in your diagram depending on how many steps you have. Okay, so if you have one step, you'll just go up and down. If you have two steps, you'll go up and down and up again. Okay, so depending on your reaction. Okay, so we're going to go up and we're going to do this so that we have two steps. Okay, at the top of each step, up at the top where we had eclipsed when we did those pictures, okay, this is a double dagger and it stands for transition state. Transition state is where you are partway in between here and this energy well. Okay, the energy well that's way over here, this is your products. All right, prod, how's that? For products. Okay, so these are going to be transition states. For every step, you will have a transition state where you're like in between. Okay, so you got your little molecules down here that moved around. They get some energy and they start going up to the top. When they get enough energy, they get to the transition state and then they fall back down. Okay, that's basically what this picture means. Now, what's in here, this little valley, I should say, in between, that is called an intermediate. There's a variety of intermediates that you can have. And the reaction that we've been working with, the intermediate is what? A what? Free radical. Okay? Your intermediates are typically higher in energy than your starting materials or your products. Okay? Intermediates are things that we can find. We know that they're formed, but they're very short-lived. You're not going to have a bucket of free radicals, okay, or a test tube of free radicals. They're too reactive. They don't want to remain free radicals. They get formed, and then they find something to react with, and then they go to products. Okay, so we're constantly doing that with our intermediates. They're constantly being formed, and then they're getting used. Okay, now over here where your products are, okay? if your reaction mixture, if your reaction overall has your products, I'm going to put products up here, higher than your starting material, that is endothermic or exothermic? Do you know that? Endothermic. Yeah, it won't let me write out there. Okay. I don't know that my product came out very low, but if your products are lower than your reactants at the end, that's exothermic. Okay, so the difference between here and here, which isn't very big here, is your delta H. That's your enthalpy. Okay, let me get another color here. Okay, the difference between here and here is your energy of activation. Have you seen that before? Maybe a little bit, they talked about that in Gen Chem. Okay, that's the energy that you need to get the reaction to go. If these molecules over here in the little starting material well don't get enough energy, you won't get a reaction. Okay? And we're going to draw pictures like this for a lot of our reactions. Okay? Now, sometimes the first step is the slowest step. You know that because the transition state is higher than this one. Okay? Because we have two steps. All right? So the slowest step is called the rate determining step. Have you heard that? Okay, good. So in this example, the rate determining step is the first one. If it was the second one, that mountain would be higher than the first one. Okay? Make the sense? The thing about rate determining steps is those are the slowest steps, and that is where you get your kinetics from, the rate determining step. So if you know a mechanism and you know what the rate determining step is, you can figure out your kinetics. Okay? And we'll be doing that as we go. I think that's everything I was going to tell you. Okay, so energy of activation is the energy needed to attain reaction, to get it going. Okay, so here would be, I'm going to draw a one-step reaction. Okay, so this is going to be potential energy, and then down here will be progress. Ooh. Let me try this. Yeah, that works better than my finger because it doesn't like my Band-Aid. I cut my finger yesterday. All right, so I'm going to draw a one-step reaction. So how many mountains do I have in my diagram? Just one. Okay, so here it is. Okay, what's over here? Starting material. What's down here? Products. Okay, so when we're doing specific reactions, we're going to put those things in there. And what is up here? What is that? It's called the double dagger. What is that? Transition state. Okay, that's it. So if I say label delta H, can you do that? We'll do a little practice on that. Okay. There we go. We use orange. Okay, if we're going to label delta H, that's going to be from here to here. Okay, that energy change. And you can actually figure that out using those tables and stuff. You did that enthalpy thing in Gen Chem. Okay, what is the energy of activation? From where to where? It's from here to here. There are people who study this and actually try to figure out where all these levels are. Okay, we're not going to. Okay, Now, what if you do this? You put a catalyst in there. How does that change your picture? It makes your activation energy lower. Here, we'll use light blue. Let's try that. Oh, what the heck color do I have? I have no idea. Okay, so your starting material and your products are the same, but your activation energy is now lower. Okay, that's because a catalyst does what? It speeds up the reaction without being used up. That doesn't mean it isn't used, not used up. Typically, a catalyst will change form somehow, and then it gets reformed. Okay, so remember what a catalyst does, because we'll talk about that too. Okay, so lowers your energy of activation, speeds up the reaction, and there are reactions that are so slow, if they don't have a catalyst, you'll never get a product. You'd be waiting for a long time. Speeds up the reaction, does not, that was an M there, I know I put it, get used up. And there's different kinds of catalysts that we'll talk about as we go, okay? Are you with me so far? Okay. Okay. A transition state is the highest energy state in a molecular collision that leads to a reaction. Okay? It's unstable, it can't be isolated. It's that in between where you're like taking that step, okay? Is that in between. An intermediate is a species that exists for a finite period of time, but that finite period of time is not like 20 minutes. All right, it's like 20 milliseconds, okay? Okay, and remember that the rate limiting step or the rate determining step is the one that has the highest transition state. Okay, it's the slowest step. It's the one that is limiting how fast anything can go. When you put in a catalyst, you lower that. Okay? Is it all coming back to you now? Okay, where is the rate limiting step in a reaction coordinate diagram? If I asked you to find it, how would you find it? I don't know how that'll show up. Let's try to make my writing skinnier. We went up to 21, right? All right, did everybody hit? Make sure your thing is working. Okay, there we go. Yep, it's the lowest point, or the highest point, not the lowest. But I'm like, wait, somebody picked lowest. It's not lowest, it's highest, okay? Okay, a negative heat of reaction indicates which of the following, do you remember? There you go. Negative was exothermic. Okay. Positive is endothermic. Okay, what does it mean to be exothermic? You're giving off energy. Okay, when you draw your reaction coordinate diagram, where's your product? Lower than reactants for exothermic. Okay, halogenation of alkanes. Okay, we talked about halogenation of alkanes with methane, the simplest one. Now we're going to move on up to some real molecules. Okay, we only do this with chlorine or bromine. Turns out that if you do it with fluorine, it's kind of explosive. So we don't really do that. There's other ways to put fluorines in molecules. And if you do it with iodine, it's really slow. So chlorine and bromine are the only two that at all work well. There's other ways that you can put iodine and fluorine in there. There's a whole lot of other ways you can put chlorine and bromine in there too, as you will see. And all the reactions do the same thing. They're going to substitute a halogen for a hydrogen. Okay, so do you see how I have this written with this RH? Okay, that R stands for an alkyl group. So like methyl, ethyl, propyl, isobutyl, T-butyl, any kind of alkyl group, even a cyclohexyl. Okay, and then there's this H over here. Okay, then we're going to add X2. X is going to be chlorine or bromine. Okay, you have to use heat or H nu. You remember what H nu was? It stands for light. You remember Planck's constant? H is Planck's constant. Okay, so you have to give it the right light. Okay, and then usually if you sit it out in a room or by a window, you will actually get the reaction to go. Okay, if you don't have heat or light, if you put it in the dark, in the cold, you won't get a reaction. Okay, it's important that you remember that you have to have these two things. Okay, and now what we're going to do is we're going to swap a hydrogen for a halogen, just like we did in the methane reaction. Okay, so notice that we get this, that's our product, and then this is also formed, HX. Okay, we'll go back over it in case you forgot how that gets formed. We're going to go back over it. Okay, so here is butane. Okay, plain old butane. We are going to add chlorine to it. Okay, with H nu. Now, do you see that I have butane written here and then I have an arrow? At the top of the arrow, I put Cl2 and underneath I put H nu. A lot of times, we don't balance things. Okay, we just want to know what happens to the organic molecule. If you're doing a mechanism, you got to worry about that a little more. But if you're just talking about what happens, we tend to not deal with the whole balancing thing. Okay, if we're going to do it in the lab and calculate yield, then we'll worry about it a little more. Okay, so when you add chlorine, we're going to substitute what for what? What's going to get substituted on that molecule? A Cl for a hydrogen. Okay, everybody got that part? Okay, now I'm looking at that thing and there are 10 hydrogens. Which one? Methane only had 4. Okay, can you tell me how many possibilities there are to substitute 1 hydrogen and 1 chlorine? How many possibilities do you think there are? Okay, let me ask you this. If I substitute a hydrogen off this end or a hydrogen off that end, are they the same or are they different? They're the same, right? Do you see how there is symmetry in this molecule? Okay, so if I do either one of those, that's one product. If I do either one of the 2 CH2s, that's a second product. There are going to be 2 possible products. Okay, so here's one of them. So which one did I substitute the chlorine for? A hydrogen on the end. Okay, that was one. So do you think you know what the bottom product is? It doesn't matter which CH2 you pick because of the symmetry in the molecule. Okay. I happen to pick the second one, which is the second carbon, which is the first CH2, methylene. Okay, so we substituted a chlorine for a hydrogen. Okay, now comes the big question. We get both. Okay, which one do you think is major? You thinking the top one? Why? Just give me a reason. There's a lot of ways to think about it. You could go, well, there's 6 hydrogens versus 4. So maybe because there's more, that one would be major. Okay. These guys are kind of inside. Maybe they're harder to get at. We'll take the ones on the ends. Okay, well, here's what it is. It's being a butthead. All right, we'll just do that. It's 28 to 72. The bottom one actually was more. Okay, let's see. Is this one going to work? Oh. Okay. The big thing to learn from this is that when you use chlorine, you get mixtures. You get all the possibilities. Okay? And it's hard to predict which one is going to be major. Okay, so let's look at this one. Oh, here we go. I didn't realize that was coming already. Gosh, I'm getting my load and then question. Take what we did on the last one and apply it to this problem. Yep, it's C. Okay. What does the reaction do? It substitutes a chlorine for a hydrogen. Do you see that all 6 of those hydrogens are the same? It wouldn't matter which one. So if you wrote Cl, CH2, CH3, that's the same thing as that. Okay. This is one. So we are substituting a chlorine for a hydrogen. Okay. All right. Now I know we got more. Okay. So a lot of this has to do with that intermediate that's formed. Do you remember what was formed? A free what? Radical. Okay. Free radicals are stabilized by electron donating alkyl groups. Okay. So an alkyl group is another carbon. Remember when we talked about, is it primary, secondary, tertiary? Okay. That's going to matter now. Okay. So here is a carbon right here, the purple carbon, and it has one, oh, this is actually the free radical one. I misinterpreted my picture at first. Okay, hang on. All right, so we'll make a green one. Here's my green carbon. It has how many carbons attached to it? Just one, and then it has 2 what? Hydrogens. Okay, so you have a CH3 out here. That's your alkyl group that is donating electricity into here, electron density, to help stabilize that free radical. Okay, free radicals are secondary, or are carbons that are trigonal planar. Okay, and up here, it's hard to see. Okay, you have an sp2 hybridization, and in that p orbital is your free electron. Okay, in order to be tetrahedral, you have to have 2 or more electrons to change from trigonal planar to tetrahedral. That can be in a bond or it can be just 2 electrons. Okay, so free radicals have 1 electron. Remember that they don't have a charge, right? I know, the hardest thing ever. Okay, so this carbon over here, the one that's purple, okay, this one, okay, it is sp3 hybridized, right? So we have sp3 orbitals coming out in a tetrahedral, okay? And then up here is our hydrogen with its little s orbital. This area is going to donate electron density through space. That's what this is showing. It's donating electron density through space. So that is what is referred to as hyperconjugation. Induction is through the bonds. Okay. We talked about induction back when we were talking about why things are more acidic than others, and we talked about like electronegativity. This is similar to that, okay? Except we're donating electron density through the bond to this carbon, okay? To help stabilize that free little electron, okay? So induction is through the bonds. Hyperconjugation is next door through space. And what is resonance? Do you remember doing resonance forms? Okay, yeah, where you can alter how the electrons are arranged. That's resonance. This example does not have resonance. Okay, there's no resonance there. Okay, now, let's see, is that gonna? Yeah, I gotta be on this thing. Okay, tertiary free radicals are more stable than secondary, than primary, than methyl. So what does the difference between this one there's the tertiary free radical and the primary one that's in that picture? What's the difference? What do we got? We got what? 3 methyls, and that one only has 1 methyl. So why would having 3 methyls make you more stable? Well, you're going to have more what? Induction. You're going to have electron density going through the bonds from all 3 of the methyls, not just 1. You're also going to have hyperconjugation on 3 spots. So here's your flat free radical. Here's your p orbital, and you've got a methyl here, a methyl here, and a methyl here. And all 3 of those can do hyperconjugation through space to help stabilize that p orbital with its little lone electron. Okay, so tertiary, and so secondary is in between. Why? What is this? That's just a little methyl free radical. Okay. We made that when we did the methane halogenation, okay? That poor little methane free radical doesn't get any induction or hyperconjugation. It's really high energy. It's really hard for it to be formed, okay? But the tertiary ones are going to be a lot easier. So as you increase the alkyl groups on the carbon that becomes the free radical, you increase the stability of the intermediate. I guess what I want to say. Okay, so which free radical is the most stable? Okay, let's do the bottom one first. I should have switched. All right, so this one is what kind of free radical? I feel like I can't read my own writing. What? Tertiary. What's this one? Primary. Which one do you think is more stable? Tertiary. Okay, it doesn't matter that this has 3 carbons going out. There's only 1 next door to the carbon with the free radical. Okay. Okay, this is a tertiary, that's a primary. Okay, now look at the top one. What kind of free radical is the first one? Secondary. What's the second one? Ooh, what's different about it? The double bond. Who has the double bond? This one does. Okay, so look at this. Oh, there we go with the lovely pen not working. Okay, you remember how many electrons it takes to make a bond? 2, right? Okay, that's important because one of these electrons and this one from the free radical will make a bond. What happens to the other electron in this double bond? It goes here. Okay, so that gives me nowhere to write. Another reason this should have been on the bottom. So this one is stabilized by resonance. Okay, this one is not. Okay, remember when you do resonance structures, you can move electrons that are lone pairs or free radicals, or double bonds, or lone pairs on heteroatoms. You can move those too. Okay, so in order to move it to stabilize the free radical, it has to be next door. So if you had this compound, I'll make it like really far. Okay, that one does not have resonance stabilization. Okay, because it's too far away. You got to be like right there. Okay, right next to the double bond, to the free radical, in order to help stabilize it. The double bond has to be right next to it. Does that make sense? Okay. Okay, how you feel about those? Yeah, that's all right. You get more practice as we go. Okay, so let's look at 2-methylpropane. Okay, how many possible products are there from that one? How many do you think? And if you're having a hard time with that, I'll give you some tips on how to know. How many? Who says 1 possible product? Who says 2? Who says 3? Who says 4? Who says 522? Nobody. That was wise. Okay, let me make a model of the starting material because that will help. One thing you can do to help you decide if the things are the same or not is to draw the product and come up with a name. Now, that doesn't mean you got to name it right. Okay, but if the names are the same, they're equivalent. Okay, so here is, I'm not going to put all the hydrogens on the methyls. Is that okay? Okay, so here is my compound. If I replace this hydrogen with a chlorine, that's 1, right? Everybody got that one probably. Okay, what about the methyls? Are the methyls the same or are they different? If I replace a hydrogen on this methyl with a chlorine, okay, that would be 1-chloro, 2-methyl-propane. Okay, if I replace a hydrogen with a chlorine on this methyl, it's 1-chloro, 2-methyl-propane. What about this one? It's the same thing. All 3 of these methyls are equivalent. Even if, as it's written on the board, it doesn't necessarily look that way. They're all the same. Okay? They're helping? All right, so there's how many possible products? There's 2. Okay? So that's how you decide. You look at what's the same. We'll do some more practice on that. Okay, so now we're going to replace one of the hydrogens from one of the methyls. Now, it wouldn't matter which one you picked. If you pick the top one because it's got the bond, who knows, and you wrote CH2Cl, that's the same thing as this one. Okay, we're still having issues seeing things the same and different, I think. All right, now the bottom one is going to be what product? What do you think it's going to be? We're going to replace this H with a chlorine. Okay, we're going to do the swap-a-roo thing. Okay, could you draw it? Okay, is that what you did? Good. Okay, which one do you pick to be major now? The top one or the bottom? Why?
The primary, other one's the tertiary.
Mm-hmm. And what intermediate gets formed? It's all free radical. Okay, so this one is 37 and this one is 63. Okay, the problem isn't the stability, but that you have stability and you have 9 of those hydrogens. People have tried to come up with a mathematical way to figure out which one's going to be major by taking into account how many hydrogens. It doesn't work very well. Okay, the big thing to remember with chlorination is that you always get mixtures. It doesn't matter if the free radical is more stable that's formed, okay, on the organic molecule. Okay, the problem is chlorine is very reactive. So what do we do about it? Well, what would happen if you did this reaction and you wanted this compound down here? You would have to do this, and then you'd get to separate it by fractional distillation. Does that sound fun? Not at all. And I'm someone who's done a lot of fractional distillation. Yeah, it is not fun. So what you really want is you want a reaction that's going to give you all this, or 99% that, okay? And what we do is instead of using chlorine, we use the other one that works, bromine. Bromine is more selective, less reactive than chlorine. It might take longer, like an extra day, but you save yourself a week of fractional distillation. Heck, let's go for it. All right, why aren't I going to the next page? Okay, so bromination is less reactive and more selective. The relative rates of radical formation by a bromine radical at 125 degrees are tertiary 1,600 times as fast as the primary. Secondary is 82. Okay, so if you have a compound like, let me get something to write here. Where did I do it? Like this. Okay, what kinds of hydrogens do we have on this? We have primaries, we have secondary, and we have tertiary. If you do this with chlorination, you're going to get all of the possibilities. But if you do it with bromine, don't forget your H nu. It's a funny V. It's like a Greek letter. Okay, what's going to happen is you're going to get this one. Almost exclusively, because it's 1,600 times more reactive to pull this one off than the other one, just by changing from chlorine to bromine. And depending on what you're doing, a lot of times it doesn't matter what halogen you have on there, okay, as you'll see as we go through the course. But bromination is less reactive but more selective than chlorination, okay? Okay, so here's our butane now. Okay, remember that how many possible products are there going to be? 2. Okay, so we're going to get that one. That doesn't want to change for me. Okay, that's the one on the end, and this is the one in the middle. Okay, basically the same 2 that we got with the chlorination. Okay, only we have a bromine there. If we're reacting with bromine, make sure bromine ends up on your molecule, not chlorine. That's why. All right, now which one do you pick to be major? The bottom one. Amen. Look at that. 98%. It's a whole lot easier to clean that up if you have to. Okay, so a lot of why this happens is because the initiation step for bromination is endothermic. You have to give it a little more energy, whereas the initiation step for chlorination is exothermic, and it just goes crazy. Okay, and so that's part of why this is like this. Okay, now the next slide has this one. You're writing? What were you writing? Oh. So what we'll do on Monday is we're going to do the whole bromination mechanism to help you remember how it all works. It's the same as the one we did for chlorination. Okay? Except we're going to use bromine. Okay? But we'll do the initiation of all the steps because we're not going to have time for that today. Okay, so look at this molecule up here, and I want you to tell me how many possible products you think there are. How many possible? Okay, who gets 1? Who gets 2? Who gets 3? Who gets 4? Who gets 5? Okay, so here we go. Okay, so give me one that you know. 1, right? Everybody picked that one out. Okay, what other hydrogens could be substituted? Okay, these 2 methyls over here are the same. Okay, so that's 2. Okay, what about this methyl? 3. What about this one? 4, 5. The 2 CH2s in the middle are different, right? This one is next to the tertiary carbon and a secondary carbon. This one's next to the secondary carbon and a primary carbon. They're different. Okay, so your little point of symmetry to look at when you look at this. Ooh, what did I do? I have no earthly idea what I did. All right, I want another color. Okay, is going to be right here. Okay, these 2 are the same. So you get 1, 2, 3, 4, 5. There's going to be 5 possibilities. But which one is going to be major by far? How many do you think there is?
You said those 2 are the same.
These 2 methyls are 1, 2, 3, 4, 5. Okay, look. Oh, actually, I could leave that there. Okay, here's 5. Okay, either one of these, that's 1. Either this hydrogen is 2, 3, 4, 5. Do you see that the 2 CH2s in the middle are different? Sometimes people want to group all the methyls together and all the CH2s together. That only works if they're identical. This molecule does not have a plane of symmetry right through it, does it? Okay, the only symmetrical spot is right here with these 2. Okay, so that should help you learn it. Okay, so your major one is which one? Yeah, that H on the top. Okay, look at this. They got a 76% yield overall. Okay, and then there's your other bill. I'll put that up at the beginning and let you write it down on Monday. How's that? All right. Good luck with homecoming. Don't get wet. Okay, so that is number. And then we're going to write out the mechanism.